A rigid square sits stationary. It is smaller than a postage stamp. It contains 0 moving parts. It houses 0 chemical batteries. It consumes 0 combustible fuel. Engineers at the Massachusetts Institute of Technology bolted this exact unit to a rooftop exhaust flue. They locked it in Cambridge. They subjected it to the thermodynamic deficit of a New England winter. It survived. Exactly 200 years after magnetic deflection exposed the underlying physics, the concept circulates digitally. An $18 version of that square is pressed against an attic roof. The digital narrative assumes infinite electrical generation, without structural limits, without municipal permits, without financial cost. The Massachusetts Institute of Technology did not engineer a miracle. They executed a controlled measurement. They analyzed an object available for digital purchase today. The acquisition cost is exactly less than a large pizza. What did MIT document? What is the precise electrical yield of an $18 square on a standard roof? Why is this architecture absent from domestic infrastructure? The variables require isolation. The math provides the verdict. The physics were isolated in 1821. Thomas Johann Seebeck at the Prussian Academy of Sciences constructed a closed circuit. He fused 2 dissimilar metals. He applied thermal energy to a single junction. The local magnetic field deformed. A nearby compass needle deflected. The mass assumes invisible intervention. It was merely structural displacement. Seebeck hypothesized a direct translation between thermal input and magnetism. His causal framework was inverted. A thermal gradient across asymmetric materials forces an electron current to flow autonomously. It requires 0 battery load. It requires 0 ignition spark. The temperature differential is the engine. Subsequent institutional analysis corrected the vector. The phenomenon retained his designation regardless. It is the Seebeck effect. In 1834, Jean-Charles Athanase Peltier documented the inverse function. The architecture is identical. The input is reversed. You force electrical current through the identical metallic junction. The system does not generate voltage. The system physically relocates thermal energy. Heat is stripped from one surface. It is deposited on the opposing plane. This specific reversal operates modern solid-state cooling today. The $18 module is a direct mechanical derivative. The cooling array inside a mini-fridge operates on identical physical law. They are functional variants born from related 19th century observations. This mechanism predates the incandescent light bulb by 60 years. It predates municipal electrical grids by exactly 1 century. The public assumes this technology vanished. It did not vanish. It integrated perfectly into operational infrastructure. The function shifted. The visibility dropped to absolute 0. Analyze the thermocouple. The sensor inside a kitchen oven. The monitor in a car engine. The regulator in a coffee maker. It does not simply read heat. It measures the fractional Seebeck voltage generated between 2 dissimilar wires. You inhabit a space governed by this thermodynamic principle. You have never known its classification. Analyze the internal architecture of the square. A thermoelectric module requires specific geometric configuration. It utilizes paired semiconductor columns. The material types strictly alternate. They are compressed between 2 planar ceramic plates. A continuous conductive trace wires them in a zigzag formation. You elevate the temperature of the primary plate. You maintain an ambient baseline on the secondary plate. A thermal imbalance is established. The charge carriers inside the semiconductor lattice react to the energetic gradient. They diffuse. They migrate laterally from the high energy state toward the thermal deficit. Forward momentum exceeds the rate of return. This unidirectional drift constitutes electrical current. The flow is continuous. It ceases only when thermal equilibrium is reached. Commercial modules priced between $8 and $18 utilize a specific substrate. The internal compound is bismuth telluride. This semiconductor is intentionally selected because it outputs functional voltage at standard atmospheric temperatures. It is not engineered for industrial thermal extremes. It requires standard operational conditions. There is 0 rotational torque. There is 0 combustion. There is 0 mechanical degradation. The internal components lack physical mass displacement. The architecture is entirely static. The structural principle is identical to a mini-fridge cooler. The thermodynamic cycle is simply inverted. You do not supply electrical voltage to transfer thermal mass. You supply thermal mass. The mechanism ejects electrical voltage. The Massachusetts Institute of Technology finalized their data. The results reside in the MIT Institutional Archive. It is not unverified digital folklore. It is documented physics. In 2008, a designated engineering team at MIT isolated a specific variable. Campus structures continuously hemorrhage thermal energy. The objective was capture. The goal was the direct conversion of escaping heat into functional wattage. Thermoelectric generators provided the required mechanical profile. The construction is solid state. They lack kinetic failure points. They possess the structural integrity to endure external atmospheric exposure. They can be mounted. They can be abandoned. The installation was executed. The team secured a diagnostic thermoelectric module. They bolted it directly to a rooftop exhaust flue. The site was the MIT cogeneration plant. This facility maintains central load. It distributes municipal electricity. It regulates climate control for exactly 80% of the university footprint. The unit was left exposed. A complete New England winter cycled through. The objective was not power. The objective was patience. The researchers monitored material degradation. The researchers quantified the precise electrical yield under unshielded atmospheric conditions. Watching a genuinely simple physical structure survive atmospheric decay forces a secondary question. Does an optimized thermal environment exist? The MIT conclusion shifted the architectural parameters. An external flue bleeds energy into open air. A pressurized hot water line isolates the thermal gradient. Interfacing the module with the water line directly increases capture efficiency. The waste heat translates at a drastically higher conversion rate. The Massachusetts Institute of Technology did not validate a domestic miracle. They validated absolute physical law. This exact architecture functions. This exact hardware resists atmospheric decay. It survives external deployment. The raw mathematical yield supersedes digital fabrication. What is the precise electrical output of an $18 square affixed to standard residential roofing? Academic researchers isolated this exact variable. A controlled field study connected 192 thermoelectric modules. They covered exactly 1 square meter of exterior roof and interior attic space. They recorded the electron flow for a 24-hour cycle. The data is absolute. The morning yield is nominal. It measures between 6 and 14 milliwatts. The curve elevates during peak solar irradiation. The afternoon maximum records between 217 milliwatts and 1 neowatts. The solar gradient collapses. The evening output crashes back down to single digits. Divide the maximum yield by the unit count. A singular module generates between 1 and 10 milliwatts under optimal solar load. This is not continuous device charging. It is not the digital narrative. Standard phone charging requires multiple watts to initiate electron flow. A basic light-emitting diode requires single-digit milliwatts. This is the absolute physical ceiling. Establish a comparative baseline. Engineers analyzed a dedicated thermoelectric module. They bolted the unit directly to a motorcycle exhaust pipe. This is a violent thermal environment. It maintains an average differential of 49 degrees Celsius. The electrical yield was measured. It registered significantly below half a watt. A residential attic presents a minimal thermal gradient. It cannot mathematically exceed a combustion exhaust system. Peer-reviewed analysis evaluated modules embedded in commercial building facades. The maximum recorded output halts at 100 milliwatts per square meter. The ceiling is rigid. Evaluate dedicated solar thermoelectric generators. The architecture is engineered specifically for atmospheric capture. There are 0 supplementary lenses. There are 0 reflective concentrators. The maximum documented laboratory efficiency terminates below 5%. This is not a fraudulent transaction. The physics are functional. The output is microscopic. The original digital broadcast recommended structural scaling. It suggested wiring 24 modules in parallel alignment. This specific claim aligns with thermodynamic reality. A synchronized array of 24 units approaches 1/4 of a watt at maximum solar exposure. It allows a slow trickle charge into a chemical battery over a 12-hour cycle. It cannot illuminate a standard room. It is simple math. When aerospace engineers require mission-critical power, they reject the $18 module. They select a nuclear substrate. The Voyager probes and Mars rovers operate on radioisotope thermoelectric generators. The mechanism utilizes the exact same Seebeck effect. The system converts the thermal decay of plutonium-238 into continuous voltage. It operates billions of miles from centralized utility grids. The physics are identical. The solid-state machine is identical. The thermal input is simply scaled to a functional mass. The anomalous behavior occurs in the absence of solar radiation. The sun descends. You align a flat, blackened planar surface directly toward the atmospheric void. The surface radiates its internal thermal mass outward. The emission velocity exceeds the ambient absorption rate. The surface temperature drops below the surrounding atmospheric baseline. This is the precise thermodynamic process that forms ice crystals on a car windshield. It occurs even when ambient air remains above freezing. Persian engineers manipulated this exact physics. They constructed Yakchal towers. They manufactured ice in a desert environment. They utilized nothing but structural geometry and the radiative void of the night sky. You position a thermoelectric module beneath that chilled plate. You expose the opposing side to the ambient ground temperature. The thermodynamic cycle inverts. The electron flow reverses. The deficit shrinks. Electricity is extracted purely from the thermal vacuum of the sky. This is not theoretical mythology. Shanhui Fan and engineers at Stanford University constructed this exact architecture. They deployed it on their structural roof. They published the mathematical yield. The initial 2019 prototype logged 25 milliwatts per square meter. It required a clear atmospheric window. The output successfully powered a basic light-emitting diode. The Stanford team optimized the geometry. They modeled a revised configuration utilizing standard commercial hardware. The calculated yield exceeds 2 watts per square meter. The architecture scales by a factor of 100. The fabrication is ongoing. The projected output can maintain environmental sensors. It can supply a phone battery. It operates entirely off-grid. The documentation belongs to Stanford. It is verified. It is peer-reviewed. It is openly distributed. It is not classified data. This is the final evaluation of the $18 module. The physics are exactly 200 years old. They are absolute. The MIT Rooftop trial confirmed the daytime parameters. The Stanford radiative generator confirmed the nocturnal parameters. The digital exaggeration is false. A singular unit outputs milliwatts. It does not power a residence. The math is fixed. You array 24 units in a parallel circuit. You can slowly charge a battery cell. You can illuminate an LED. You can maintain a small sensor. This is functionally valuable for isolated deployment. It is not infinite free electricity for a domestic structure. It never will be. If physical deployment is required, the data dictates location. A standard roof is inefficient. A functioning wood stovepipe presents a massive thermal delta. The temperature gradient is violent and stable. This is why isolated populations tap the stovepipe. It requires a severe heat source. It requires structural proximity. You do not utilize the roof shingles. Zero data was suppressed. The documentation is stored in the MIT Public Archive. The physics are detailed in open-access academic journals. It lacked commercial marketing for a precise economic reason. You execute a single $18 transaction. The hardware requires zero maintenance. The unit never breaks. It does not generate a recurring municipal utility bill.